Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. And today we're looking at lesson 3.8, which involves problems with energy and momentum. So we have to use both of these, conservation of energy and conservation of momentum, in solving some of these kinds of problems. So I will take you through one particular type of example, and we'll go right through from start to finish with this example right here. We'll put some numbers in here in a minute, but what this is an older kind of setup whereby they're able to measure the to get ballistics information in terms of the velocity of a bullet that's fired from a gun. And what happens is they shoot it into some ballast that's hanging from some string or rope or whatever it is. And upon impact, the bullet lodges within the ballast itself, and then it swings up to some particular height. And then based upon the data that's gathered, they're able to determine the velocity of the bullet after it's fired from a rifle or a handgun or whatever, as the case may be. And so now that I'm sure they have more sophisticated equipment to do that now, but this was actually fairly reliable equipment, and was used. This sort of setup had been used for quite some time. So let's put some numbers in here and look at each situation. There's actually two phases to this. The first phase is where the bullet collides with the ballast, and in this case it's just a hanging mass, and the bullet collides with it, and it embeds itself right within the ballast itself. So this is one of these collisions that's known as a perfectly inelastic collision, because the two objects stick together after collision. So with the collision, whenever you come across collision, think conservation of momentum. And we'll talk a little bit about why you don't think energy initially with the collision. We'll talk about that in just a minute. Afterwards, however, after the bullet lodges within the ballast and the two objects move together, once they're in motion, okay, after the collision, that's when you can think conservation of energy. And that's because in the collision, when the bullet embeds itself into the ballast, you actually lose some energy because the ballast actually becomes deformed in some way, whether this is a block of wood or something else. Because the fact that the bullet is lodging itself within it, it takes energy in order to deform the matter, what this is made out of. And so you lose some energy due to heat and whatnot. So the collision itself is not conservation of energy. However, it is conservation of momentum. But then after the collision, immediately after the collision, once the two objects together are in motion, then you can think conservation of energy. So the object then swings up, so all of its kinetic energy then becomes potential energy. And based upon the data they get, that's how they can determine the initial velocity of the bullet. In this case, however, what we're going to do is we're actually going to, so we first got the mass of the bullet, which is 0.2028 kilograms or 28 grams. And we have the velocity of the bullet. It's 230 meters per second. And we have the mass of the ballast, 3.6 kilograms. And we have the length of the rope that it's hanging from, which is 2.8 meters. So what we're doing with this kind of a problem is we want to know, after the collision, how high do the two objects together end up from their starting position? How high does the object end up? And we use conservation of energy to do that. So first we'll look at the collision, which is conservation of momentum. And the initial momentum is just going to be the mass of the bullet times its velocity. And then after the two objects stick together, then it's going to be the mass of the two of them together times the final velocity. So I'll just put the numbers in there now, and then we can easily calculate that. So just working through the math now, basically. And we get the final velocity of the two objects together then is 1.78 meters per second. All right, so now immediately after the collision, the two objects together are moving in this direction at 1.8 meters per second. All right, so now that we have that established, now after the collision, immediately when this object starts to move at 1.8 meters per second, now we can use conservation of energy in order to determine how high the object goes above the starting point. So we use conservation of energy in that case, and so what's happening is all of the kinetic energy is being converted into potential energy, and so once it reaches its maximum height, that is all potential energy. And so we just simply use that equation then. So the initial kinetic energy has to equal the final potential energy. So we just put the numbers in there, and we work it out mathematically. The masses cancel out, of course, and so we just work it through this way, and we get 0.16 meters. 0.16 meters. So after the object moves and it swings this way, then it reaches a maximum height of 0.16 meters above the starting point. So we can use the conservation of energy after the object starts to move, but we can't before and after the collision, immediately and after the collision, because as we mentioned, the bullet loses some energy when it embeds itself into the ballast, whatever this is, a piece of wood or something. Some energy is lost by deforming the wood itself. However, once it starts to move, then once the two objects move together, then we can use conservation of energy. So you have to understand when it is that you can and cannot use conservation of momentum or conservation of energy. And so anytime you see collision itself, think conservation of momentum. This kind of scenario here, think conservation of energy. All right, we're going to take this a little bit further, and sometimes you will be asked for, well, what's the final displacement vector of the two objects together, the bullet plus the ballast? And so we can calculate that as well. So what happens is the bullet comes along, it embeds itself into the ballast, and the two objects together swing to some point over here, to a maximum height, which we calculated to be 0.16 meters. And then just using a little bit of a geometry, we can actually determine this length right here, and thereby find what the final displacement vector is of the bullet plus the ballast together. So I'll just use a little bit of geometry here now. And so we know this length, the length of the rope, is 2.8 meters. And if that's the case, if this is 2.8 meters, then this length from here to here has to be 2.8 minus 0.16, which is 2.64 meters. So from here to here, 2.64 meters. And then we can find the angle as well now. We have enough information to find the angle. And so we're dealing with similar triangles. Once again, you can work all this through yourself if you're unsure about which angles are going to be equal, but with a little bit of geometry you can show that these two angles are equal. And so we can find the angle now. It's going to be the inverse cos of 2.64 over 2.8. So that'll give us the angle, which is 19.5 degrees. And so now we have this angle right here. And so it's pretty easy then to find out what this length is right here. Actually, we could find the hypotenuse right away using the inverse sine. I'm not sure which way did I go here. So actually, I first found this length here. You don't actually have to do that. You could use the inverse sine function to take you there directly. I used the long way, but hey, that's okay. So from here then, we can find out what that length W is, which is 0.45 meters. And then from there, just use Pythagorean theorem then to find the hypotenuse of that triangle right there. As I said, I'm doing it the long way, but that's okay. And so then the hypotenuse then is 0.48 meters. So therefore, the displacement vector of the ballast, the final displacement vector of the ballast plus the bullet is then given by this. It's 0.48 meters at 19.5 degrees north of east. And we had calculated that angle previously. So sometimes you will be asked to actually find what the final displacement vector is. So again, using both conservation of momentum with the collision itself, and then afterwards, in this kind of a scenario, you're using conservation of energy in order to solve this kind of a problem. And also using a lot of algebra and geometry and all the math that you have learned already. Some trigonometry is thrown in there as well. So we have just about everything in there. And that's why these kinds of problems, they draw upon many of the skills that you have learned throughout your career so far.